Hi everyone, I'm Ashaq Sharafuddin from Muhammad bin Zayed University of Artificial Intelligence, UAE, and University of Colombo. It's a pleasure to present our CVPR 2025 highlighted paper titled O-TPT, Orthogonality Constraint for Calibrating Test Time from Tuning in Vision Language Models. In this work, we focus on improving the reliability and trustworthiness of vision language models by addressing their poor calibration during test time adaptation. Vision language models like CLIP have unlocked incredible zero-shot capabilities. To push this further, test time prompt tuning (TPT) was introduced to refine prompts using only inference data. While TPT improves accuracy, it also exaggerates model confidence, making prediction appear more certain than they actually are. This is especially risky in medical imaging or autonomous systems where model must know when not to trust themselves. Prior methods like CTPT try to fix this using feature dispersion, but they ignore the geometry of embedding space, particularly angular relationships. Our core insight is that cosine similarity or angular distance between class text features strongly correlates with calibration error. When text features are too close in direction, the model tends to be overconfident. But when we enforce greater angular separation, the model makes predictions that are better calibrated, meaning its confidence reflects its true accuracy. Now let's look at the figure on the right hand side. This plot shows that the probability density of the cosine similarity between class-wise text features. Notice how better calibrated prompts results in distribution skewed toward lower cosine similarity, meaning greater angular separation. This directly supports our intuition. More orthogonal prompts lead to lower calibration error. And now figure on the left hand side takes this idea further. It shows the relationship between average cosine similarity and ECE across 80 different handcrafted prompt styles. Each point here presents a different prompt evaluated across 7 datasets. And you can see a clear trend as cosine similarity drops, ECE decreases consistently. This confirms that angular structure not just features norm or dispersion, it's critical for reliable calibration. To formalize our idea, we introduce O-TPT, a method that adds an orthogonality constraints to the text feature metrics used in test time prompt tuning. This constraint encourages the class-specific text embeddings to be mutually orthogonal, meaning they point in maximally different directions. In technical terms, we minimize the cosine similarity between class vectors. This constraint is added as a regularization term to the original TPT loss, allowing the model to not just optimize for accuracy but also for angular separation. Now let's look at the figure which compares the feature geometry of CTPT and OTPT. You see how CTPT enforces average text feature dispersion using L2 norms. It pushes features away from the centroid, but as a result, the features can still lie close together directionally, leading to poor angular diversity. On the other hand, you see how OTPT's angular constraints solve this. Instead of pushing features radially outward, it ensures they are evenly spread across directions, covering the hyperspherical surface and avoiding collapse into narrow clusters. This shift from L2 dispersion to explicit angular optimization enable better utilization of the feature space, and as we show in the experiment, it leads to significantly lower calibration error, especially in hard to generalize scenarios. And importantly, OTPT is fully test time applicable. It doesn't require labels, retraining, or any supervision, making it practical and scalable across domains. We conducted extensive evaluation using both CLIP VATP16 and CLIP ResNet 15 backbones. We tested across fine-grained datasets like food, Stanford cars, Oxford pets, DTD, generic datasets such as ImageNet and Caltech, distribution shift datasets like ImageNet A, R, V2, and Sketch. We measured both accuracy and two key calibration metrics such as expected calibration error and static calibration error. Let's look at the results. For fine-grained tasks on VITB16, ECE drops from 11.6 to 4.21. On ResNet 15, ECE drops from 11.7 to 5.45. When utilizing the train weights of Cube as a baseline at test time, ECE drops from 18.36 to 7.91. For Maple, ECE drops from 6.94 to 4.11. For distribution shifts on VITB16, ECE drops from 12.0 to 4.88. On ResNet 15, ECE drops from 16.7 to 9.69. Across both transformers and resonators, O-TPT outperforms CTPT and TPT, consistently reducing calibration error while preserving accuracy. To visualize calibration, we use reliability diagrams. In these plots, perfect calibration appears along the diagonal. CTPT tends to deviate significantly, showing underconfidence in some cases and overconfidence in others. O-TPT predictions, however, lie much closer to the diagonal, indicating that predicted probabilities better reflect actual correctness. In summary, O-TPT introduces a lightweight, effective method to calibrate VLMs during test time. By enforcing angular diversity through orthogonality, we make the model less overconfident, especially in difficult or shifted domains. O-TPT work across multiple backbones, require no supervision, and can be plugged into any test time prompt tuning framework. This makes it an attractive candidate for real-world deployment where reliable confidence estimates are essential. Furthermore, we are currently exploring several existing directions. First, dynamic prompt regularization, where we adapt the strength of orthogonality based on the task uncertainty or input distribution. Second, deploying O-TPT in safety critical applications like radiology or autonomous navigation, where miscalibrated confidence can have real consequences. We also see potential to extend this method to newer multimodal architectures beyond CLIP. Our poster will be presented in Exhibition Hall D, poster 394. You can find us on Saturday, June 14th from 5 p.m. to 7 p.m. Thank you for listening. You can find our code on GitHub at the QR shown here and feel free to reach out via email for collaboration or questions.